So chapter 17 is called Aqueous Ionic Equilibrium. There's another quote here. In the strictly scientific sense of the word, insolubility does not exist. And even though substance is characterized by the most obstinate resistance to the solvent action of water, may be properly designated as extraordinarily difficult of solution, not as insoluble. So really, everything dissolves a little bit. Part of why water is known as the universal solvent, because it does just sort of eventually get to everything. But most of the first half of this chapter, everything we're going to get through today, is still acids and bases. So specifically buffers. So you probably know that antifreeze is dangerous. I don't know if you've ever smelled antifreeze. It has a very sweet smell. And hopefully you've never tasted it, but it also has a sweet taste, which is why it's really, really dangerous to just throw it out or leave containers open when you're disposing of it, because it will attract animals, cats and dogs, or other wildlife who will come and drink it because it smells sweet and tastes sweet. But it's an alcohol that your liver metabolizes into glycolic acid, which alters the acidity of your blood. And it's kind of funny because your liver is really good and kind of has a mechanism to process everything, but sometimes it's the processed product that's bad and not the actual molecule. Methanol is another example of that, where the methanol itself is not toxic to you as much as the oxidized product of methanol, which I think is formaldehyde, or it might be another formic acid. So this blood pH, if you know stuff about medicine, is very, very critical to maintain within really tight limits, right? So for humans, it's 7.36 to 7.42. Oh, I just hit my elbow. And that blood pH is maintained by a buffer, specifically a buffer of bicarbonate and carbonic acid. So large enough quantities of glycolic acid in the blood can overwhelm the buffer capacity of your blood and start your blood pH plummeting, becoming more and more acidic. Similar thing happens, well, the process is known as acidosis. It can happen if you're diabetic. You can get into diabetic ketoacidosis, where your body is starting to produce lots of acidic ketones. That'll also shift your blood pH. One of the problems with this, and there are many, many, because your blood is everywhere, so if the pH changes, it affects everything, is the hemoglobin, or the ability of hemoglobin to bind to oxygen, right? So if we increase the concentration of H plus hydronium, it's going to shift this equilibrium to the left, so forcing hemoglobin to give up oxygen rather than bind it and carry it to the rest of your body. The treatment here is actually the same as if you get methanol poisoning. I think it's the same probably for a lot of toxic alcohols, is you give the person ethanol. So your body can safely process ethanol, and I think it's a competitive inhibition. So you just give the person a shot of vodka, and then their liver starts processing that, and there's more of the ethanol than there is of the methanol, so it slows down the processing of the methanol into toxic byproducts. And then your kidneys can excrete the methanol. But back to buffers. So the pH of most solutions changes significantly when acid or base is added, right? You've done titrations before with strong acids and strong bases. Buffers, though, resist pH change. They do this because they've got an equilibrium. So buffers contain significant amounts of a weak acid and its conjugate base. All right, the conjugate base of a weak acid is a weak base. So you've got these two in equilibrium with each other. Just a weak acid by itself or a weak base by itself will not contain of the conjugate base or conjugate acid to act as a buffer. So you can't have just one. You have to put both into solution at the same time. So a buffer typically consists of a weak acid, acetic acid is one, and then if you add also sodium acetate, then you increase the concentrations of both of those, and they sort of counterbalance the concentration of the other. So if you add any acid to this, it gets neutralized by the sodium acetate, or if you add a base, it gets neutralized by the acetic acid, and those concentrations don't change very much, and therefore keep the pH the same. So which of these solutions is a buffer? Really, which one has a weak acid and a weak base? Weak acid and weak base of the same kind. Yeah, D. So we've got nitrous acid and nitrate, sodium nitrate. All of the rest of these, well, this is nitric acid and sodium nitrate, right? Strong acid. So the conjugate base of a strong acid is going to be pH neutral. And then this is nitrous acid, which is a weak acid, but then sodium chloride is just a strong electrolyte, has no effect on pH. Nitrous acid and hydrochloric acid is a weak acid and a strong acid, so that's just a lot of acid. So yeah, D is going to be the only one there that has a weak acid and its conjugate base. So if we have a solution that initially contains 0.1 molar acetic acid and 0.1 molar sodium acetate, so we've got significant quantities of the weak acid and the weak base. The presence of the acetate ion causes the acetic acid to ionize even less than it normally would, resulting in a less acidic solution than if you just had acetic acid by itself. And really, the opposite is happening also, right? If you just added sodium acetate to a solution, the presence of acetic acid is preventing that from stealing hydrogens from water to form more hydroxide. And so that common ion effect is what causes the balance. So you couldn't put two different weak base, or you couldn't put a weak base and a weak acid that were not conjugates of each other into a solution to form a buffer. They have to have a common ion effect in order to maintain those high concentrations and maintain the pH. So you can calculate the pH of a buffer solution, and this is going to look just like any other ice table that we've done. I will say you can technically write this either way with Ka. So you're starting with, so if we write it with Ka, it'll be acetic acid plus H2O in equilibrium with H3O plus the acetate ion. And then if we flipped this, we can use Ka and Kw and calculate Kb, and we could solve it using Kb and the equilibrium for that base. There's no reason to, though, because we were given Ka, so might as well just use that. So 0.200 molar, practically no acid to speak of, and then 0.100 molar acetate. So that'll be our initial, and then our change. And actually, ask this question too. How do we know which direction that this is going to change? It might be something that we just kind of take for granted because I keep writing it that way, but how could you determine which way this equilibrium is going to shift? Or which way it's going to shift to get to equilibrium? So that has more. So saying it's because this is 0.2, but we've got a really negative Ka. So do you think that's enough? There's a way we can tell for sure. We can calculate for a particular letter, Q, right, so if we wanted to calculate Q for this reaction, we'd get the concentration of H3O plus is 0 times the acetate over the acetic acid concentration. So because we have nothing for hydronium on the product side, we're going to have to fill that gap, because right now our Q is 0. And so K is larger than Q, so we're going to shift to the right. So then because we're shifting to the right, then this is going to be negative X plus X plus X. So 0.2 minus X, X, and 0.1 plus X. And then our Ka. So again, this is the equilibrium expression. And it's going to be X times 0.1 plus X divided by 0.2 minus X. Okay, so do you think it's safe to assume, yes or no, do you think it's safe to assume that X, the change in X, or the change in our initial concentrations is 0? That we can make the small x approximation? Yeah. Because our concentrations are fairly large, our Ka is fairly small, so we can say that this is not going to increase significantly, and this is not going to decrease significantly. So then it's just going to be 1.8. Let me do this first. 1.8 e to the negative 5 times 0.2 divided by 0.1. So 3.6 times 10 to the negative 5 equals X. So then our pH, because X is just going to be our H3O plus concentration. So we do the negative log of that 3.6 times 10 to the negative 5. Yep, and that gives us 4.44 as the pH. Standard stuff. Now, are there any questions so far? Should be good. Still doing equilibrium. Still doing ice tables. Should all be familiar. Buffers, though, in calculating the pH of buffer solutions is useful enough that somebody derived an equation. As you can see right here, the Henderson-Hasselbalch equation is specifically for buffers, and specifically for when buffers, or when you can make the small x approximation for buffers. So if we write this as the equilibrium expression, Ka equals the concentration of H3O plus A minus over the concentration of HA, and actually I need to move this over here so I have more space. Right, so that's just the equilibrium expression. The way that you get to the Henderson-Hasselbalch equation is you take the negative log of everything, because if you take the negative log of Ka, that'll actually give us pKa. So write this out first as negative log of Ka equals the negative log of H3O plus times A minus over HA. Right, all of this in here. And then we can use that special property of logs, that if the log of something multiplied by something inside of the log function, it's the same as the log of the thing plus the log of the other thing. So this can be instead log of Ka equals the negative log of H3O plus And because this is because it's the negative log, we have to distribute that negative. So it's minus the log of A minus over, yeah. Wait. I did this slightly different when I did it earlier, because we need to end up with I think this is plus. No, it is negative. Okay. Right. Damn it. This is going to be plus the log of the base over the acid. And I have negative log. I'm pretty sure we have to distribute this. So let's just keep going with this for now. Because the negative log of Ka is going to become just pKa. And the negative log of H3O plus is just pH. No, we don't distribute that. It is just yes, okay. Because we're going to subtract pH on both sides, and we're going to subtract this pKa. So this is the log of, yeah, A minus over HA. And so this is minus the log of A minus over HA. So I subtracted pH from both sides, subtracted pKa from both sides, because ultimately we want to be able to calculate pH. And then if we just multiply everything by -1, or multiply both sides by -1, I should say, then we'll get the pH equals the pKa minus the log, or plus the log of A minus over HA. I should have trusted the math. Because I think the way the book derived it was slightly different. Yeah. Okay. So this is the first thing that we're getting that can save us from doing ice tables if we have buffer solutions. So the Henderson-Hasselbalch equation is useful as long as the small x, the x's small approximation is true or valid. And then, so initial concentrations are not too small, and x is or k is fairly small. So the acid and base are greater than 100 to 1,000 times larger than k. So if we've got like 0.1 for each of for our acid and our base, then our K could be something like times 10 to the -3, and we could still be okay with the X's small approximation. But you can always do an ice table and get the correct answer. This is just, again, kind of like that other sort of equation that I showed you for when the X's small approximation is true for like regular expressions where you just have one reactant. You're trying to figure out how much product is going to be formed. You can always do the equilibrium approach to get the right answer. this is just a shortcut if you know when to use it. I don't know if it says this in the textbook. There's also an interesting relationship here, at least I think. So when the concentration of the base is the same as the concentration of the acid, then the ratio between them is 1, and it's the log of 1. Right? So the log of 1 is 0, and this is log base 10. So when the base and acid have the same concentration, the pH of the buffer solution is the same as the pKa. So if we have pH equals pKa plus the log of 1, right? Log of 1 equals 0, pH equals pKa. So that's a special scenario that's going to be useful. And is another shortcut, right? If you have a buffer solution and it asks, oh, what's the pH of this buffer solution? Concentrations are the same, gives you the pKa, pH is pKa. And the opposite is true, or I guess not the reverse, but if you modify this so that it's for POH, so POH is equal to the pKb plus the log, I think this switches so that it's the acid over the base. And you can derive that one also, or you can just really rearrange this. Okay, moving on. The Henderson-Hasselbalch equation, very useful. So we want to calculate the pH of a buffer solution that's 0.25 molar HCN, 0.170 molar in potassium cyanate. For hydrocyanic acid, our Ka is 4.9 times 10 to the negative 10. And our pKa is 9.31. So we're going to do both the equilibrium approach and the Henderson-Hasselbalch approach to just show that this is true. So our equation here is going to be HCN plus H2O is H3O plus Cn minus cyanide, and then 0.250, leave out water. This is 0.170. So it's our initial change. And again, because there's no acid already in the solution, we know that we have to go towards that 0 in this equilibrium. So this is going to be minus x, x, x. And then set this up like we have 1,000 times before. So x times 0.17x, or plus x, over 0.25 minus x. Do you think that our x's small approach is going to be valid? Yeah. K is times 10 to the negative 10. Oops. So we can assume that these are going to be 0. So 4.9 e to the negative 10 times 0.25 divided by 0.17. Where can I write this? Here, we can write it here. So that's 7.2 times, use a little more than that, 7.20588 times 10 to the negative 10. And we want the pH. So the negative log, that big number, equals 9.14. 9.142. Oh, I guess Ka only had 2 sig figs. All right, now observe how much time we save. So Henderson-Hasselbalch equation, pH equals pKa plus the log. And one way to think about it, to keep straight whether or not it's base over acid or acid over base, this is something that I know I struggled with all the time. It's just like the equilibrium expression where it's products over reactants. So we're working with Ka, so Ka is our reactant, the conjugate base is our product. So it's still products over reactants here. So this is the concentration of the base over the concentration of the acid. So pH equals our pKa, which is 9.31, plus the log of 0.17 over 0.25. So 9.31 plus the log of 0.17 divided by 0.25. pH equals 9.143. Should technically only have two sig figs. So remember, pH, pKa, all of these logged, negative log values, because they're logs, only the decimal places count as significant digits. So 9.31 still only has two sig figs. Any questions? Cool. We press on. So calculating pH changes in a buffer solution. So buffers resist change because any of the added hydronium or hydrogens get picked up by the conjugate base. Any added base gets picked up and neutralized by the acid. So there are two steps to these problems. The first part is to do the stoichiometry calculation, so figure out how the addition changes the relative amounts of acid and base. Because as we've seen now in the Henderson-Hasselbalch equation, right, the pH of the solution is almost entirely dependent, aside from the pKa, is entirely dependent on the ratio of base to acid. So if we change that ratio, we need to figure out how much it changes by, and that'll change our pH calculation. So once you've done that, then you can calculate the equilibrium, or you can do the equilibrium calculation, which is the ice table, or the Henderson-Hasselbalch equation. So if a buffer contains the weak acid HA and its conjugate base, A minus, the weak acid has a pKa of 4.82, and the buffer has a pH of 4.25. Which statement is true of the relative concentrations of the weak acid and the conjugate base in the buffer? So think about what the negative log, or what the log, because it's plus the log of base over acid. So remember, if these are the same, then pH is pKa. And we know our pKa is 4.82, but the pH is 4.25. So what happens if you put in a number larger than 1 in a log function? Just take your calculator and say log of, let's do 1.5. Yeah, so log of 1.5, larger number, is going to be positive. So if this was like, what did I say, 1.5? So if this is if the base has a concentration of 1.5 molar over a concentration of 1 molar, that's going to be a positive 0.176. So you get a positive number there. So what happens if we put in a number that's smaller than 1? So let's say our base concentration is 0.5, and then 1 molar still for the acid, right? So now less base than acid. So the log of 0.5 is negative 0.301. So our pKa, or pH here is less than pKa. In the Henderson-Hasselbalch equation, there would be pKa plus the log. So is the acid concentration greater than the base, less than the base, or the same? What was it? Did you say something? Or was it a squeaky chair? The concentration of the acid? Yeah. Concentration of the acid is greater than the pH. Because our pKa here would be 4.82, and it would have to be some number less than 1. And that's ratio between the base and the acid can only be less than 1 if the acid is more than the base. And it makes sense, too, if we have more acid in the solution, our pH is going to be lower because it's making it more acidic. If there was more base in the solution, the pH of the solution would be higher. Right? Acidic solutions are low pH, basic solutions high pH. So actually, just for kicks, we could actually figure out what the ratio of acid to base is here. So if we plug in the pH, which is 4.25, equals our pKa, which is 4.82, plus the log of base over acid. So 4.25 minus 4.82 is negative 0.57. So if I do 10 raised to the negative 0.57, our ratio of base to acid, I guess I'll put here 10. The base to acid ratio is going to be 0.269. So there's roughly 4 times as much acid as there is base. Or what? Yeah, 1/4 of the amount of base as there is acid. So when we're doing the stoichiometry calculation, if we take something like a buffer here, and we've got 0.1 molar in both the acid and the conjugate base, we'll calculate the pH after adding 0.025 moles of strong acid. So the first thing you have to do is make sure you calculate everything here in moles, because this is stoichiometry, not an ice table. So this is 0 moles of acid, it's 0.1 moles of base, and 0.1 moles of acid, or weak acid. So we add in 0.025 moles. That's going to get consumed, so it'll go back to about 0, and it gets neutralized, I should say, by the base. All right, so this conjugate base gets used up a little bit. Now it's not concentration, but number of moles is 0.075, and the number of moles of acid has gone up, the conjugate acid, or the weak acid, right? Because any of that A minus is getting converted into HA. And then once we have those numbers, then we can convert them back to molarity, which is easy when it's 1 liter, and do a ice table. So adding a small amount of strong acid is equivalent to changing the initial concentrations of the buffer. So we've just reduced our amount of base, increased our amount of acid, and now we're just running a ice table with those new concentrations. Oh, so yeah, it's weird. Just weird that this is here like this. So our calculations can be done in moles because the volumes are the same and thus cancel out. So here, and this is what will maybe be tricky and might throw you off if you're doing problems in ALEKS, although ALEKS will definitely make you do different volumes all the time, every time. But if you do have different volumes, so if you add solid to a solution, we can add a solid base to a solution, it's not going to change the volume. But as soon as you start mixing different volumes, so if you have half a liter of your buffer, you add half a liter of some concentration of base, now your concentrations have all changed. And you need to recalculate those. And you need to do the stoichiometry in moles and the rest of the calculations in molarity. So here we're just showing the opposite. So if you're adding a strong base, then it's the exact opposite of adding a strong acid, and we're just converting acid now into base. So anytime you add a strong acid or strong base to a buffer solution, all you're doing is changing your initial concentrations that you put into your ice table by the number of moles of strong acid or strong base, not the molarity. Sometimes it works out to be the same as molarity, but it's not always. So if we add a small amount of strong acid to a buffer, we convert a stoichiometric amount of the base to conjugate acid, which creates more acid. And because we have more acid than base, our pH goes down, just by a small amount. Adding a small amount of strong base does the opposite. Again, a stoichiometric amount of acid is converted to conjugate base, and we increase the pH. And actually, take a step back here. So when we added and did this stoichiometry calculation, notice that this is written out as the base in the product side. That's getting used up, to produce that acid. When we come over here to do the equilibrium, we flipped that back to the way that we've been doing it, where the acid is the reactant and the base is the product. So this is just a nice little visual of adding an acid or adding a base. So in scenario A, we add 1 hydrogen in. And so we've got 4 buffer weak acids and 4 conjugate bases. So when we add that hydrogen, it takes one of the conjugate bases, turns it into an acid. And so now we've got 3 to 5. Opposite happens when we take hydroxide, steals one of those protons, so now we have 3 weak acid molecules and 5 conjugate base molecules. So which image best represents the amount of hydroxide added to the buffer in part B of the figure? So on this side. How much hydroxide was added? Just 1. So if you're just counting these, it might look like 2 are added. But that's just because 1 was taken from the acid and added to the base. So it's sort of a net switch between those absolute numbers of 2. One decreases by 1, the other one increases by 1. But it is just one of these being converted. Right? So that means that there was 1 base molecule added. All right, so if we have a buffer solution, conveniently, a 1 liter buffer solution contains 0.100 moles of acetic acid and 0.100 moles of sodium acetate. And then this is where it just gets thrown in here because the initial concentrations are equal. The pH is equal to the pKa, which is 4.74. So calculate the new pH after adding 0.015 moles of sodium hydroxide. So we're going to take our 0.100 moles of acetic acid. And how does adding How does adding 0.015 moles of sodium hydroxide change your concentrations? What happens to the acetic acid? Decreases. All right, so it's going to decrease by that amount. Oops, strong base. So then our concentration of the acid after that is going to be 0.085 moles, which I think is our concentration, our amount of acid. And then our conjugate base will increase by exactly the same amount. This will be plus. So it's going to be 0.115 moles NaC2H3O2. And then do you think our concentrations are still large enough that we can use the Henderson-Hasselbalch equation? Save ourselves the trauma of an ice table? Yeah. Right, so we're still at least 100 times larger in both concentrations than the Ka, which is times 10 to the negative 5. So the Henderson-Hasselbalch equation is going to be pH equals pKa plus the log of the base over the acid. So pH equals, the pKa is 4.74 plus the log of our new base concentration. So here technically we should be converting it into concentrations, but we have 1 liter, so molarity is moles per liter. It's going to stay exactly the same. So 4.74 plus the log of 0.115 divided by 0.085. So pH equals 4.87. And if you wanted to later, you could prove that the equilibrium method would give you exactly the same answer. I think one of the things I remember doing buffers is I thought you had to do either the equilibrium or the Henderson-Hasselbalch equation. But no, it turns out you could do either. So, confused myself a lot for no reason. No questions? Still good? All right, so buffers containing a base and its conjugate acid. So we can also have buffers composed of a weak base and the conjugate acid of that weak base, like ammonia. Because remember, ammonia in water is actually H4OH. Well, NH3 and then NH4OH, or it's NH3 plus H2O. So calculations are similar to buffers containing weak acid, but for the Henderson-Hasselbalch equation, you have to use pKb. As I mentioned earlier, you can calculate pKb, and uses actually the same relationship. Didn't derive it like this before, but pKa and pKb are also related the same way that pH and pOH are. So then when you calculate, though, using this, you're going to get pOH equals pKb plus the log of, and just like for the regular pKa, pH Henderson-Hasselbalch equation, right? It's products over reactants inside of that log. So here, because the reactant is now our base, this is actually the log of the acid over the base. because it's the same equation for the reverse reaction. And also important to remember that it calculates POH. All right, so exactly the same. If I went back to the same thing we saw for weak acids, weak bases, weak acids, weak bases is the same. We've got equivalent amounts of ammonia, or not exactly, it doesn't have to be exactly equivalent, but fairly equivalent amounts of ammonia and ammonium chloride. So weak base and a weak acid. And then the common ion effect helps keep them in those concentrations.